Hi guys, in this video we're going to have a look at tree diagrams, and in this particular video we're going to have a look at when we've got independent events. So when it says independent events, all that means is that when you do the first event, it has no impact on the second event. Okay, they're completely independent, they don't affect each other, and then we call them independent events. So for example, if we look at this one here, so Dave has 10 coloured cubes in a bag, 4 are red, 6 are black. He picks up a cube at random, notes the colour, and key thing here, he replaces it. Okay, so when he puts it back in the bag, when he then does it for a second time, obviously he's still going to have 4 red and 6 black. So the first event, which is him picking a cube for the first time, does not impact him picking it out for the second time because he puts it back. Okay, so what we can do when we've got a question like this and we're asked for the probability of getting a red or 1 red and 1 black and at least 1 red, is we can draw a tree diagram. Okay, so it pretty much just looks like a branch of a tree as opposed to an actual tree, and this is how we do it. So first thing we do is we go, okay, for the first event, or first pick, because obviously he's picking a cube. So for the first pick, he's got 2 outcomes. So I draw 2 branches like so. Okay, and he's got 2 choices. He can get a red, or he can get a black. So as you can see here, 2 choices, red, black. And then what we can do is we can put the probability on the branch. So if he's got 4 red out of 10 possible cubes, we say that's 4/10, and obviously 6 black, so it'd be 6 out of 10. Now what you'll notice is because I know both outcomes, red and black, there's no other possibilities, it's definitely going to be red or it's definitely going to be black, that the branches, the probability on the branches should add up to 1. So if I have 4/10 plus 6/10, obviously that'll be 10 over 10, which is 1. So that's a little check you can do to make sure your probabilities are correct. Okay, so if that's 4/10, that's 6/10, they add up to 1. So that's the first pick. And then obviously here it says he does it again. Or sorry, here it says he does it again. So exactly the same thing. If he picked a red, he could then, on his second pick, I'll put second pick here, get exactly the same. He could get a red, or he could get a black, or from the first one he could have picked a black, in which case second pick, exactly the same options, he could pick a red and a black. And because he replaced a cube, I'm still going to have 4 red, I'm still going to have 6 black. So the probabilities are going to be exactly the same. 4 out of 10, 6 out of 10, 4 out of 10, and 6 out of 10. Again, the branches here add up to 1, branches here add up to 1. So that's how you draw the tree diagram. But how do we use that to work out the probabilities? Well, it's nice and easy, because all we do, if I want to work out the probability of getting a red and a red, which I do, all I do is I multiply across the branches. So I'm going to do 4/10 times by 4/10. And you might remember from my multiplying fractions video, or you might just remember how to multiply fractions, we just times the top. So 4 times 4 is 16, and 10 times 10 is 100. So probability of getting red is 16 out of 100. Now some of you might be saying, should I simplify that? Well, unless the question says to, I would always leave it, and I'll show you why at the end. Okay, so I'm going to leave it like that. I'm going to work out the probability of all of these now, just so you can see what I'm doing. So 4/10 times 6/10 would give me 24 over 100. This one here, black and red, so 6/10 times by 4/10, again will be 24 over 100. And then black, so 6/10 times 6/10 is 36 over 100. So the reason why I don't simplify is this. If you wanted to work out the probability of getting 1 red and 1 black, I have 2 options. I can get red and black, or I could get black and then red. So there's 2 possibilities of what I can do. So I've got this probability and this probability. So what you do in this case, if you've got two different ways, or more for that matter, we add the probabilities. Now remember, when you add fractions, the denominator, the bottom number here, needs to be the same. So because I haven't simplified, my denominator is already going to be the same. So it's really easy. I can just do 24 over 100 plus 24 over 100, which will be 48 over 100. Happy days. Exactly the same thing with this one. This time it's at least one red. Okay, so it's a slightly different word. Here I wanted one red and one black. Here it's saying at least one red. So for this one I could have red, red, because at least one of them is red. Let's put that down. 16 over 100. I could have red, black, because again, at least one of them is red. So 24 over 100. And this one here, black and red, again, at least one of them is red. And I can't have this one because black, black, obviously they're both black, so not at least one of them isn't red. So I can't have that one, but I can have the rest. So all I then do is add those up. Be 34, so 64. Yep, 64 over 100. And you're done. Okay, so that's the first example of how to set up a tree diagram and how you work out the probabilities. Just a quick point here. If you look at the end ones, again, because these are the only four outcomes that you can have, red, 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 black, black, red, black, black, these here will also add up to 1. So 16 over 100 plus 24 over 100 plus 24 over 100 plus 36 over 100 will be 100 over 100, which of course is 1. Because remember, probabilities, if you know all the outcomes, need to add up to 1. Okay, so that's that example. Let's just do another one. So with that last one, we had fractions. I just want to do an example where we have decimals, so you can see exactly how we do it. The method is still exactly the same, it's just the probabilities are with decimals. So in this example, during a circuit, Mr. Thomas and Mr. McKelvey do press-ups and a run. The probability that Mr. Thomas will win on pull-ups is 0.7, and the probability that Mr. McKelvey wins the run is 0.9. So I've got two events here. One of them is press-ups, and the other is a run. So let's start with press-ups. And I've got two choices. Mr. Thomas could win, so Mr. T could win, or Mr. McKelvey, so Mr. M could win. And let's read the probability. So the probability that Mr. Thomas will win on pull-ups is 0.7. So I put 0.7 on the branch. Now, I'm not told what the probability of what Mr. McKelvey is. However, from the previous example, we know that the branches need to add up to 1. So if that's 0.7, to get to 1, it has to be 0.3. Right, that's the first one done. The next one was the run. And again, Mr. T could win, Mr. McKelvey could win, Mr. Thomas could win, or Mr. McKelvey could win. And let's have a look at the probability here. So the probability that Mr. McKelvey wins is 0.9. So Mr. McKelvey would be 0.9. And again, branches need to add up to 1. So that would be 0.1. And obviously exactly the same down here, 0.9 for Mr. McKelvey winning, which means 0.1 for Mr. Thomas winning. So that's how you would draw your tree diagram. And how would you work out the probabilities? Exactly the same way as if you had fractions, we just times along the branches. So 0.7 times 0.1 is 0.07. Next one would be 0.7 times 0.9, 0.63, 0.3 times 0.1, 0.03, and then lastly 0.3 times 0.9, 0.27. So key thing to remember with decimals is this is where people always go wrong. When they do 0.7 times 0.1, they think it's 0.7. Just be really careful, it's actually 0.07. Why? Well, if I just, let's go just a bit down here. If I do 7 times 1, obviously I get 7. So I've moved the decimal point once, twice. So my answer, I need to move it back once, twice, which is why it goes to 0.07. Same with down here, 0.3 times 0.1, 0.03. So just be careful. That seems to be a very common mistake when people are doing tree diagrams with decimals. Anyway, let's get into the questions. So what's the probability that Mr. Thomas wins both? So Mr. T, so it'd be 0.07. Probably that Mr. McKelvey wins just one. So obviously we can have Mr. Thomas winning the first one, Mr. McKelvey winning the second one. So it would be 0.63. And I could also have Mr. McKelvey winning the first one, but then losing the next one. So that would be plus 0.03, which of course is 0.66. And the final one here, probably that Mr. Thomas wins at least one. So we could have win-win, which would be 0.07. You could have win-lose, which is 0.63. Or he could lose-win, which is 0.03. And if we add them all together, we have 0.73. Okay, so that's just an example using decimals. I've got one more for you guys. Oh, again, just very quickly, these here will all add up to 1, just as these would all add up to 1 as well. So again, it's a little check that you can do. Okay, last example. So we've looked at when we have 2 events, just to show you it works with more than 2 events. Here I've got 3 events. So a rugby team plays 2 games. Using the tree diagram, work out these questions here. So I've drawn the tree diagram here just to save a bit of time, so otherwise this would take a little while. So there's 3 outcomes when playing a game: win, draw, lose. So that's for the first game, and I've just made up some probabilities here. Notice again, they all add up to 1. And then, of course, the second game, win, draw, lose for each of the possibilities. And again, I've just made up some probabilities here. So exactly the same. These all add up to 1, all add up to 1, all add up to 1. So to work out the probability of winning both games, so win, win, I'll do 5 over 20 times 7 over 10. So 5 times 7 is 35. 20 times 10, 200. So I'm just going to work out the probabilities for all of them. As you can see here, I've just already written it out of multiplying across the branches. So next one would be 10 over 200, maybe 5 over 200, 77 over 200, 22 over 200, 11 over 200, 28 over 200, 8 over 200, and 4 over 200. And again, if you were to add all these up, it would be 200 over 200, which would be obviously 1. Okay, so there's all the different possibilities or different outcomes we could have. Let's start going through it. So we said win-win was 35 over 200. Exactly 1 win, so I can't have win-win because I want exactly 1 win, so that's out. But I could have a win-draw, which we worked out was 10 over 200. I could have a win-lose, because again, exactly 1 win. I could have a draw and a win. And then finally, I could have a lose and a win. And if you were to add them all up, I believe you get 120 over 200. Okay, so that's how you do that one. And this one here, at least 1 win. So I could have win-win, win-draw, win-lose, draw-win, and lose-win. So let's write them out. So I'll have win-win, because at least one of them is. So that's 35 over 200. Win-draw, that's 10 over 200. Win-lose, that's 5 over 200. Draw-win, and then lose-win. So you'll notice that actually they're all the same as this one, apart from the win-win, because the question is at least 1 win, whereas this one was exactly 1 win. And if you add all those up, we're going to have 155 over 200. Okay, guys, so that's just an example of if you have 3 outcomes, you just draw an extra branch, and you just do exactly the same thing. So key things to remember: branches add up to 1, or in this case, whatever the denominator is, so it'd be 20 over 20, which is 1. It's like the same thing here, here, and here. Once you've got all the outcomes, these again will all add up to 1. And if you want to work out the probability, we multiply across the branches. And then when you're answering your questions, just be really careful of the language used and make sure you only pick the branches that are relevant to the question. Hopefully that helps, guys. Cheers.